Welcome everyone to today's panel discussion on the future of batteries. My name is Laurent DeJambry. I'm the Assistant Dean of College Relations and Development here at the College of Chemistry, and it is my pleasure to introduce today's talk. Today's panel discussion is the first event of our recently launched Berkeley Energy Ecosystem, which is part of a greater initiative to further engage you through various Berkeley ecosystems where you can learn, explore, and connect with Berkeley faculty, alumni, students, and industry innovators on relevant topics. This year, we are launching our first 4 of our ecosystems focusing on biotech pharma, energy, food tech, and advanced materials products and technologies. Our next event is on Wednesday, December 16th at 11 a.m. and will be a lightning talk on green products by Marty Mulvihill, College of Chemistry alum, co-founder and executive director of the Berkeley Center for Green Chemistry, and founding general partner for Safer Made. We invite you to join us for those future talks. And we invite you to learn more about Berkeley ecosystems at ecosystems.berkeley.edu. Now for a few logistical matters regarding today's discussion. Today's panel discussion is being recorded, as were all past events and future events. In the coming days, the recording will be made available on the website at ecosystems.berkeley.edu. We are planning to field questions today towards the end of our discussion, so please use the Q&A function as opposed to the chat function to share any thoughts or pose any questions to our panelists. And finally, directly following our event today, you'll receive a short survey from us. Please take a moment to give us feedback on today's discussion, but more importantly, to give us some input on future topics that might be of interest to you. Okay, if energy powers our economy, batteries keep it running. And thus, it is my great pleasure to introduce today's panel discussion on the future of batteries and our discussion facilitator, Professor Bryan McCloskey. Bryan is the Vice Chair of Graduate Education and Associate Professor of Chemical and Biomolecular Engineering at Berkeley. Bryan's research focuses on electrochemical energy storage, electrocatalysis, and corrosion-resistant materials. And Bryan has won numerous awards in electrochemistry. Thank you, Bryan, for agreeing to participate in our panel discussion, both as a facilitator and panelist.
Right. Let me see here. Mute myself. Well, thank you very much, Lo, for that kind introduction. It's my privilege today to serve as facilitator, host, and as a participant on this panel as well. I'm joined by 3 fantastic researchers in our field today. And I'm going to let each one of them introduce themselves, and I'll do so with asking each of them the first question of our panel today. So could you introduce yourself, your background, and then also briefly describe projects that you're excited about at the moment? And Amy, let's start off with you.
Great, thank you very much, Bryan. I'm really happy to be part of this panel. I received my PhD from UC Berkeley from the Department of Chemistry in 2001. I was a salt state chemist in graduate school and then went on to do a postdoc learning how to do transport measurements. When I was developing proposals to start my faculty position, I was looking at, applications using advanced materials, and it seemed to me that essentially every application was being limited by the battery. So I decided that, working in energy storage and trying to contribute in that field would be really critical. I'm currently a professor in the Department of Chemistry at Colorado State University, and I'm also the founder and chief technology officer for Prieto battery. So my research interests are in trying to use naturally occurring minerals that can be sustainably sourced for applications in energy production and storage. So we work in photovoltaics, hydrogen storage, and lithium and sodium rechargeable batteries. The focus of my company is to commercialize a new architecture for lithium ion rechargeable battery using high throughput, very sustainable manufacturing methods. So we use electroplating to build our battery. We use fairly non-toxic chemistry. And the goal is to build a 3D battery that is a solid state battery that is very safe and can charge and discharge very quickly. So our particular focus is on applications that need power. So thinking about transportation and power tools, applications on construction sites, things like that. So again, thanks very much. I'm really excited to be here.
All right, thank you very much, Amy. Newt, let's go to you.
Yeah, sure. So thanks so much for having me here. It's an honor, especially that to be around these battery experts, because I don't think I would call myself a battery expert at this point, unlike all the other panelists. So my connection to Berkeley is I did my undergrad there, so I did a bachelor's in chemistry, and then I, for a couple of years, wasn't sure whether or not I wanted to go to grad school, and I was working at Berkeley Lab on biopolymers. And then I did my PhD at Columbia. So again, not on batteries, I worked on inorganic metal chalcogenide clusters, trying to assemble those into different kinds of materials. And then kind of stumbled upon a super exciting opportunity to be the part of a founding team for a battery startup that was spinning out of Columbia. So working on grid scale redox flow batteries. So really big batteries, not solid state batteries. And for the last 2 years, that's what I've been doing. So I've learned an incredible amount about the battery ecosystem, energy storage in general, kind of like what it's like being at a startup and starting from spinning that out from academia. And then most recently, I left for a bunch of reasons, for personal reasons. I've relocated to France. So I'm here now, kind of exploring different ways to connect ideas and people with entrepreneurial drive to create something new in the clean tech space.
Wonderful, thank you so much. Steve, you're up next.
Hi, so I got my PhD at Harvard and then did a postdoc at Berkeley, and I was also a visiting professor here. I spent most of my career in industry and at the Ford and General Motors research labs, and now I work at LBL. And if you want to contact me, my email address is sjharris@lbl.gov. If you look at a commercial lithium-ion battery today, you won't actually see much difference from what it looked like in 2007 when I first got into the battery field. And my research project these days aims to enable all solid state batteries, which for me means ceramic solid electrolytes and lithium metal anodes. And that would be a real change that would provide a step change in energy density. One of the big problems preventing their adoption is the presence of lithium dendrites, which can grow from the lithium to the cathode and cause a short circuit. So this is something of a mechanics problem. And it turns out that during my career at GM, I worked on the mechanics of transmission gears in contact. And as part of that work, I modeled contact mechanics of gear teeth. And since gear teeth aren't perfectly smooth, their contact is very complex because the roughness means that contact is nowhere near conformal. In fact, usually only 1% or so of the surfaces are in actual contact. So I decided to apply this modeling capability to contact between lithium metal and solid electrolytes. And one of the things I learned is that even under a megapascal of external pressure, only a few percent of the lithium would be in contact with the solid electrolyte, which is different from how the field looks at this interface. I'm also working on understanding why such a soft material like lithium can penetrate through ceramic solid electrolytes. And this has been kind of a mystery in the battery field. And it turns out that I've done some work in the corrosion field back at GM, where I knew of another soft material like water can penetrate right through another hard material like steel. Well, that problem is called stress corrosion cracking, and it's been solved. All you do is you put the surface of the steel into a state of compressive stress, and actually the same compressive stress strategy makes ceramics and glasses stronger. That's how Gorilla Glass on your iPhone works. So now I'm trying to see whether putting the surfaces of ceramic solid electrolytes can prevent dendrite penetration.
All right, thank you very much, Steve. And before we get to the next question, I'll introduce myself and my background as well. Before I came to Berkeley, I was a research staff member at IBM Almaden Research Center. I was one of 2 scientists hired into what they called the Battery 500 project there back in 2009, which was focusing on enabling lithium-ion batteries for electric vehicles. So we focused on trying to understand the electrochemistry. There was a lot of unknowns in that chemistry, and so we developed capabilities to quantitatively analyze what actually was occurring within lithium-ion batteries. And as I came to Berkeley, the ecosystem here is, I think, much more focused on lithium-ion batteries in general. And so my research has trended towards understanding different phenomena in lithium-ion batteries. So new higher energy density battery materials, enabling fast charging of lithium-ion batteries, or low temperature battery performance are some of the main thrusts. Although I still also am interested in metal air chemistries, lithium air and sodium air chemistries as well. So advanced battery materials and new electrochemistries that could supplant lithium-ion batteries as high energy density alternatives. All right. Well, with that, let's get to our next question here. And Steve, let's start off with you on this question. So we have panelists with backgrounds in startups, large companies, academia, investing, national labs. How did you find your place in the energy sector?
So for me, it's completely accidental. I was working on ductile fracture of cast aluminum at Ford. And then one day Ford announced that they'd sold all their casting plants. And so I needed to find something else. And by a freak accident, I happened to be walking past the office of somebody I knew at Caltech who was working on lithium batteries. And, you know, I told him batteries hasn't changed in 100 years. And he said, no, there's these lithium batteries. And so I started looking into it. And then at Ford, I talked to my director and he said, no, we already tried batteries in the 1990s and they'll never work. So we're never going to have a project on batteries. So by luck, GM was looking to hire battery people to restart their program. So I went there. And so that's how I got into it. And because my background is so far away from batteries, it's been interesting for me because I look at batteries differently than most people do.
All right, thank you, Steve. Anouck, how about you?
Yeah, so kind of to echo a little bit of the luck that Steve just talked about, I think for me, it wasn't my technical background at all, but there was a postdoc in my lab who had worked on this paper academically and had decided he wanted to spin out this startup. And at the end of the day, I think fundamentally a lot of battery research is chemical research. So it's like developing new molecules, new materials. And in this case, we were looking at new organic molecules that were stable electrochemically under certain conditions. So given that I had, background in electrochemistry and molecular design, there's a lot of overlap. So I kind of coincidentally made my way there and then ended up learning an incredible amount about it and kind of want to stay in this field.
Oh, great. And Amy, how about yourself?
Yeah, so for me, it started with the academic interest. And what I was really trying to figure out was a very rich project that a lot of students and postdocs could work on. And so we took the approach of, first trying to design a new architecture for a battery. And then we thought about the problem kind of backwards in terms of, first, we made a list of all the equipment we were not allowed to use. So my thought was if we were ever successful in making a 3D battery, we would want it to be something that could be scaled and could be done in, scale to large volume in a way that would be pretty environmentally conscious. And so, we had this list of equipment we couldn't use, anything that was really expensive or required a lot of energy. We made lists of all the types of chemicals in the battery industry that are really toxic or harmful to the environment. We decided we couldn't use any of those. And so I think in terms of fundamental research, the parameter space is very large. And so using, your personal interests or your personal values is as good of a way as any to limit, or to focus your research. Eventually what happened, however, is my university was trying to find ways to help faculty do more with intellectual property. And somebody in the business unit of the university heard me talk about our 3D battery, and they thought it would be a great idea for a company. I was a pretty young assistant professor, so I really wanted better equipment, and we don't have very good funding mechanisms in the US for that anymore. And so it was pitched to me as, if you start this company, there's this local angel investor who would love to invest. She was one of the first to buy a Tesla in Colorado. So she was thinking about batteries, and the idea was that I could just, use the investment to buy really good equipment and really accelerate the research. But, eventually what happens though is you have, people that are working on the project that get very invested in the idea. And so I ended up raising more money so I could hire my first postdoc and a couple of my first students as employees when they were ready to finish. And then eventually they had so many good ideas that we had to raise more money so we could hire technicians to help accelerate that development. And I will say that it's, not the way you should start a company. I think we're one of the few startups in lithium ion batteries that are trying to tackle all the parts of the battery as well as the manufacturing method. And I think there's a lot of resistance in the battery industry to change how people think about making batteries. So, it's an industry that makes enormous volumes of batteries already every year. And so to try to push a change, I think is really a challenge. It's a little bit like trying to climb uphill, but I ultimately think that's what the industry will absolutely need to do. There is no one perfect battery for every application. So I think we need to really diversify in terms of the work being done on different battery chemistries and different architectures. And that's, I think, becoming increasingly more critical that we do that efficiently and quickly, given some of the challenges with climate change. And I do think energy storage will be a part of that. So I certainly didn't mean to start a company intentionally. That was not the beginning goal, but it turned out to be a really good way to try to accelerate the development of our idea and try to get it out into the marketplace.
Thank you, Amy. Yeah, what strikes me about all of our panelists is that their training is not necessarily in battery research directly, that we all came from different communities. And I'm exactly the same way. My PhD was in water purification membranes. And I was hired at IBM to study dehumidification membranes, so gas dehumidification membranes for lithium air batteries. The idea being that you only want lithium to react with oxygen in the lithium air battery. And if you have water or CO2 or other gases that could also react, that might result in inefficiencies in the system. And so I went from water purification to IBM wanted me to study dehumidification membranes. And I got to IBM, and the electrochemistry, there was just so many unknowns and so many interesting problems to tackle there that I essentially switched entirely into electrochemistry. But my background in ion transport through materials, I think really helped serve a purpose in helping me understand fundamentals of electrochemistry a little bit more at the beginning. So yeah, it was kind of an unusual trajectory to battery research, but it's a great field, and still many problems remain. And you see just an example of the many different types of materials classes and problems that our panelists are working on today. Okay, well, let's go to our next question. Anouck, let's start with you. The importance of renewable energy is talked about more and more, particularly in connection with global climate change. How should we be investing in energy storage both for the long and short term?
Yeah, so I think for the short term, and maybe my opinion's a bit biased, but I think we should be spending a lot of money on startups and innovation at that kind of scale. I think a lot of startups recently proved that the research that they're doing can lead to a valuable product, and this is not like in the battery industry, but just looking at like Moderna. So this is like more taking the example of biotech, but Moderna's research led to concrete, vaccine. So, and I think this is an example of a startup that was funded and supported along the way. I think if we support entrepreneurs and if we support both the ideas and teams coming out of academia, but also people that don't necessarily have ideas, but give them a concrete industry need, I think in the short term, if we figure out ways to create accelerators or continue the work we're doing in that way, I think it would be really exciting. In the longer term, that's a tough question. I'm excited about nuclear energy in the long term, and I know that's a little bit of a controversial topic for energy storage, but I think to me, and I've kind of changed my mind about it recently, I think nuclear energy is quite promising for the long term. And yeah, I think there's a lot of promise with advanced new nuclear technologies and things that we could do there with advanced reactors if we funded that.
Cool. Yeah. Steve, how about yourself? What do you think about investing in short and long term in energy storage?
Oh, I agree with Anouck. I think in the battery world today, we've got thousands of scientists in academia and in industry working on developing better batteries, and they have very well-funded, well-established funding mechanisms. But industry and academia have a lot of problems communicating in the battery field, and I think the critical interface today, just like Anouck suggested, is filled by startups, and getting funding for startups is really, really hard. I'm an angel investor or on the advisory board of 4 different battery startups, and that's limited mainly by, do they want me? Because I think that's really fun, and I hope if you're interested in startups, supporting them, then invest in them if you have money, and if you don't, offer your services to them. I think that's the critical piece that needs effort.
And Amy, how about yourself as an entrepreneur who started your own company? What do you think of this problem of investing short and long term?
Yeah, I think, well, I'd like to agree strongly with what Anouck and Steve said. I think, we used to have pretty fundamental research groups in large companies. And I think because of a push to really focus on products and making money and, returns to shareholders, a lot of that research has gone away because it, on the surface appears speculative. But good science always leads to new inventions. And I think that now startups really serve that niche. I think there is a challenge in the battery industry, at least in the US, and I'm focused really just on lithium ion batteries in this statement. And that is that there's been sort of a pattern of overpromising and raising very large sums of money without producing products. And I think part of that is a rush to try to get something to market very quickly, instead of really focusing on the fundamental science and doing that part well to begin. So several of us have mentioned, we came to energy storage from various different research areas that were pretty fundamental in nature. And I guess I would argue, that the engineering that took the first lithium ion battery in the early 90s and is mass producing today is beautiful. And they have really managed to get a lot of performance gains out of chemistry that has essentially not changed. But if we want a step function change, if we really want to make energy storage, some multiple better, that really requires taking a step back and working on some pretty hard problems that have not yet been solved. And that involves chemistry and physics, material science. I mean, it's a lot of really fundamental ideas and training that have to go into these problems. And I think startups are a great place to mix people with very different backgrounds who see problems in very different ways and getting pretty creative solutions. I think then the challenge is going from a startup and then trying to ramp up production and really get to large scale. And I think that requires patience. And, it requires for the really new ideas, in the future, maybe they will be 2 times, 5 times better than what we have today. But they're not yet. And so it's really trying to appreciate the fundamentals behind the ideas that I think is going to be important.
Yeah. Yeah, I agree with that as well. You know, from my perspective, when I think of short and long-term financing funding in energy storage, I think a key question that comes to mind is, you know, is lithium ion the dominant technology for the first? It is the dominant technology for the foreseeable future. What's going to supplant it? If you look back on the history of battery science, it seems like every about 50 to 75 years, there's a new technology that comes along and supplants the old technology. So it started with Alessandro Volta, with the discovery of the voltaic pile back in the late 1700s. Then after that, the Daniel cell, which was, I think, I forget exactly the chemistry, but it was zinc-based chemistry. Then after that, the lead acid battery became the dominant battery technology in the mid 1800s. Then followed by nickel iron chemistries that Thomas Edison pioneered. And then finally, now we're in the era of lithium ion batteries, which you know, Stan Whittingham produced to practice initially back in 1970 or so.
Yeah.
And so, you know, what is next? And I think that if we had a concrete answer to that question in the energy storage community, it'd be very easy to, this question would be very easy to answer, and it isn't clear. And so I think that it's important on a long-term scale to take some risks, in new chemistries, while still in the short term continuing to push lithium ion towards its physical limits, which I think many of the battery companies, large battery companies, are doing right now. So new architectures, new chemistries in the long term are going to be very important to get to new applications like grid scale storage, which requires enormous power densities, enormous energy densities, and huge lifetimes in batteries as well. Yeah. All right, well, let's move on to the next question. This is a timely question. Amy, let's start with you on this one. How has COVID affected your work, your research, or the industry in the field as a whole?
Oh, I think that's a hard question. I think my company was very lucky in that we had just moved into larger space with the anticipation of scaling. And so, but we still have a pretty small team. And so they have been able to space themselves out pretty well. And that is important because they can still talk to each other across a room. I think, you know, these kinds of virtual meetings are exciting, and it's really cool that people are using these both for business, but also for personal life. It's a good way to be connected. But I think sometimes for problem solving, there is nothing quite like physically being near each other and bouncing ideas off. And I feel like that happens a little bit more slowly when it's electronic. I also think that investors are a little slower right now for perfectly understandable reasons to make investments. And so for startups, that often leaves us in a pretty tricky spot. We don't usually have cash reserves to be able to withstand large changes. I will say though, for energy storage, I think now that people are on their devices even more, there is a very acute understanding of why batteries are important and why you would want batteries to last longer and why you would want batteries to be safe. So I think that helps mediate that a little bit. But I think, you know, Anouck mentioned this new vaccine from Moderna, which is so exciting. I mean, there are several exciting examples, but the science that went into being able to develop a solution like that so quickly started many years ago. And so it's just another, I think, good example where fundamental research does lead to useful outcomes. It just, you never really know when it might be needed or in what way it might be manifested. And I think, Brian, your comment about what will supplant lithium ion batteries, I think that's a very hard question to answer. I agree with you that a lot of the efforts that are going into different chemistries are really important. And I guess I would say, particularly for things like trying to help tackle climate change, I don't think there is one answer. I think we need to have, it's just like how you might invest personally. You don't put all of your money into one solution. You have a pretty diversified portfolio. And I think that's what we need for energy storage. We shouldn't be just focused on one target. There should be lots of people working on potentially different solutions. So it's a really long answer to your question. I do think the pandemic has slowed down some research because of the need to space people out. I'll tell you, in my academic lab now, we have to work in shifts. They're separated from each other. So I have quite a bit of concern about the younger students not being trained as well, because they don't, they're not informally bothering their older lab mates all the time the way we normally teach. And I also think thinking about safety is even more important. So, if I have somebody who's not as experienced working in lab, I have to think through a lot more carefully what they're doing and try to anticipate risk, because I know they don't have a lot of other people just around them keeping an eye out. So it's, I think, maybe added a little bit more intention to the research in a good way. And my students, a lot of the time they spent at home when we couldn't be in lab, they spent time thinking. And so I think a lot of the experiments that have come from that are maybe a little bit better designed because they couldn't be in labs. So they had to spend time really reading and thinking first. And so that's a potential positive that has come out of all this.
Great. Anouck, how about yourself?
Yeah, so I guess when it all started happening in March, so we were a super small team, only 4 of us at this point. And so obviously, if you're a super small team and you're really early stage and you can't go into the lab, that completely stops your progress. So it's quite simple. We were just like stopped completely for a few months, as were a lot of people, I'm sure. But unlike the people around me, you can't really get much done over Zoom if you can't go into the lab and do a reaction. So that slowed us down. But at the same time, I think it allowed us to take a step back and focus on other elements that we maybe hadn't been prioritizing because we were putting R&D at the forefront. So stuff like patents, putting together some patents or putting that ahead and kind of thinking about other strategies and more, strategic partnerships and things like that. So I think for us, it slowed us down, but allowed us to focus on other pieces of the research. And then I think because we were such a small team and because our lab space was pretty big and allowed for social distancing, all that stuff, we were able to get back and kind of wear masks, have our own space, have our own offices, and kind of get back to it business as usual, not too far into the whole thing. So that's from the perspective of just XL batteries. And then it is a tough question, and I'm not super sure how to answer how it affected the industry as a whole, but just word of mouth and what I hear from academic labs and stuff like that, it just completely slows down research if you can't go in whenever you need to and you need to take shifts. I think it's important in R&D to be able to go at your own pace. So I'm sure that must really slow down most folks.
Mm-hmm.
Right. Yeah. Steve, what do you think about COVID and how it's affected research?
So it's certainly slowed down. Sorry for the phone in the background. It certainly slowed down the stuff that I've been thinking about. The ion implantation experiments that I was hoping to do to generate compressive stresses were supposed to be a year ago almost, or 9 months ago, so they haven't happened yet. As far as development, my sense is that that in industry, there's much less of an impact than in academia. For one thing, most of the industry is in East Asia, and they really have, the COVID is not such a big deal there. And so they've been able to go at the same pace as normal pretty much. The only really important battery manufacturing going on in the United States that I know of is at Tesla, and they're going full speed ahead. People are being more careful, but I don't think that it's had a massive impact on their progress.
Right. Yeah. And from my perspective at Berkeley, I think safety has taken priority throughout all of this for our students, and so the students and postdocs who work at LBNL and at UC. So we've been slowly ramping up the number of people who are allowed in lab at any given time. Fortunately for battery scientists, you can make quite a few battery cells in the lab at once and put them onto a battery cycler and allow them to cycle for a few days. And so we don't need to have everybody in the lab together at once to still make pretty decent progress in our lab. But yeah, it has been it has slowed things down a little bit, but I think that that's absolutely necessary for the safety of everyone in the lab. And I think that both UC and LBNL have taken everyone's safety as a key priority right now, which I really appreciate from the campus and from the national lab as well. All right. Well, with that, I think we will start taking Q&A from the audience. And I see that our Q&A chat section has been populated with quite a few questions from the audience. And so I'm just going to go through as many as we can here in the last about 20 minutes or so that we have today. The first question is it possible to define 2 or 3 biggest problems that need to be solved in this field? And Steve, maybe you can start us off with your thoughts on this question. What are the biggest problems you see?
So I think the single biggest problem I see is the poor communication between academia and industry. I mentioned, I think this is where startups play a big role, but there's not enough of them. Partly this is because industry refuses to divulge, their secrets to academia, partly because academics aren't working on necessarily the projects that industry cares about, which tend to be more incremental. So at a very high level, I think that's the biggest problem.
Oh, great. Amy, what are your thoughts on this? And then I'll go to the next question and have Newt lead us off on that one.
Okay. I would agree with Steve. I guess I'll focus more on the technical side. And I would say there are 2 science problems that would have a huge impact if we could solve them. One is how we discover new materials. So computational methods are getting a lot better and a lot more accurate at trying to predict new compounds that might have properties that would be really useful. The problem is those methods aren't very good at predicting materials where, like, the messiness of the material is what makes it useful. So they're not necessarily very good at computing, say, ionic conductivities as an example. But also the other big problem is even the best theoretical prediction doesn't come with a recipe. So somebody still has to figure out how to make that material and how to test it under conditions that are relevant. So I would say discovery of materials is one really big challenge, and being able to do it quickly and efficiently is really hard. And the second big technical area I think that we need to think more deeply about is how chemistry happens at interfaces. So how, say, a molecule or an ion desolvates, how it goes across an interface. And the real problem with any energy storage device is all the interfaces. So it's not good enough to have one really great material. It still has to work in concert with a lot of other materials. And so trying to understand those interactions, I think, is really a big challenge. And I think if we could make inroads at understanding that, that would have a huge impact.
Couldn't agree more, Amy. I think that that's a really important interfacial reactivity, interfacial phenomena is really important in batteries.
Yeah.
All right, let's go to our second question here. And Anouck, could you provide your thoughts on hydrogen-based energy storage?
Yeah, to some extent. I mean, so I guess hydrogen, being in Europe, you hear a lot more about hydrogen here. They're really pushing that forward. From my point of view, it's interesting because a lot of fuel cells have similar architecture to redox flow batteries. So at the end of the day, kind of come down to both sides, cathode, anode material, and also the membrane. So I think there's a lot of exciting work getting done with membrane development that can withstand the conditions of fuel cells like heat and stuff like that. I think it's a really exciting field. I think it's quite expensive producing what they call green hydrogen. So electrolyzing water. It would be a dream if we could just split water, get hydrogen, and then it's a clean fuel. But I think it's obviously much too expensive today. So in that sense, I think there's a lot of really interesting work getting done on electrolyzers and all of that. Again, to go back to the topic of startups, I think a lot of interesting startups are working on this. So yeah, I guess that's my perspective on hydrogen. I think it's exciting. I'm not sure about the economics of it, but I think it would be the dream if we could get it to work.
Yeah, and I'll give my perspective here. I completely agree with Anouck. I think that this is an area of intense research for good reason. The energy density of hydrogen as a energy storage or as an energy carrier is quite high, and so the challenges are being able to produce hydrogen at scale and a cost-effective and energy-efficient fashion as well. One thing that batteries do have an advantage over fuel cells in is energy efficiency, round trip, cycle-to-cycle efficiency. Whereas with an electrolyzer, there's an energy penalty for separating or creating hydrogen from water, and then taking that hydrogen, putting it into a fuel cell, and then having it converted back into electricity. Nevertheless, it certainly will play a critical role in the energy storage landscape in the future. And I think that that there are many applications that could be positively impacted by fuel cells. Yeah.
I'd just like to mention that one hurdle that hydrogen faces, it's really a direct competitor to electricity. And whatever the technical merits of one or the other, we already have an electric infrastructure, and we don't really have a comparable hydrogen infrastructure. So unless hydrogen, if in a case like automobiles, let's say, I mean, who knows technically which one would be better, but it'd be very hard for hydrogen to break in just because it's so far behind.
I think that's a problem with sort of like a lock-in effect where, once you have something at very large scale, it sort of blocks other potential solutions. And, when the first automobiles were being made, people claimed they would never be widespread because we didn't have an infrastructure for refueling. And obviously we solved that problem. So I think at some point, arguing that something isn't possible because it doesn't currently exist is a good way to limit us to only the solutions that we have today. And so I think there are ways where the government can be creative, where companies can be creative with incentivizing early adoption. And I think that needs to be part of any solution.
I certainly agree. It's just that that is a hurdle that needs to be faced head on.
Totally agree. Yep.
And I think there's a materials challenges in fuel cells as well. The fuel cells are typically, and electrolyzers are comprised of precious metals. Iridium, platinum are used as catalysts. No such metals exist in conventional battery materials. So that's something that if we can find new materials that could enable more widespread use of electrolyzers and fuel cells, that could also potentially go a long way in enabling those chemistries and those devices. Yeah. All right, well, let's continue. I think that let's have Amy take this next question. Can we look into a future of a battery different from lithium ion batteries? So what could supplant lithium ion batteries in your opinion in the future, Amy?
Well, I mean, I'll just daydream here. I'm not placing a bet by any means, but I think multivalent batteries would be amazing. So, you know, lithium and sodium, you only get 1 electron per atom. If we could move to magnesium or calcium, we would get 2 electrons per atom. If we could even move to something like aluminum, you would get 3 electrons per atom. There, all the challenges that I mentioned before about interfaces and transport are even more difficult. But I think that would be pretty exciting, and especially something like aluminum, where we already have really good ways to make aluminum in very large scale. But the science there is really, really hard, and that will take quite some time. I think there are companies like Toyota, for example, where, you know, magnesium is on their 50-year plan. So I think there's a recognition these are hard problems, but they would be pretty exciting. I will say, you know, unfortunately, there's no way to store charge more efficiently than in a chemical bond. And so going back to fuel cells, you know, chemical fuels are just have very high energy density. So I think, you know, Brian, getting to your point about precious metals, if we could figure out a way to not only electrolyze water more efficiently, but also to be able to use fuel cells without any of those precious metals, that would be a huge advance. That again comes back to materials discovery. And I think if we're going to develop a new technology, I would argue the very beginning is the best time to think about how would we recycle those devices. So instead of waiting for the industry to get to mass production and then realize we have a problem with, you know, sourcing these materials or, you know, filling up landfills, I think that new technology should be developed with an eye toward how to make it recyclable and sustainable. So that's, I may be skipping ahead a little bit, but I think as we get to new chemistry, that's something that should be developed, I think, in concert with the initial science.
Yeah, I completely agree, and I think multivalent is really, you know, this is a strong research effort again in the battery community to try and enable some of these chemistries that just have a lot of challenges associated with transport and trying to understand how to strip divalent ions out of their solvation shells, so to allow efficient charge transfer rates at interfaces. I think is a lot of really interesting questions still remain in those batteries. Let's continue on to our next question, and I'm going to direct this question to Steve first. What do you see as the largest bottleneck for lithium-ion battery improvements? Cathode materials at larger voltage windows, current densities, energy capacity, anode materials. What do you think?
So I think anode materials is the least bottleneck. I think silicon is coming along. There's a couple of different good-sized companies that are very close to commercializing them. You know, cathodes, you know, NMC was invented, I don't know, what, 15 years ago, 20 years ago. And, you know, I'm not sure there's been much progress. There's all, you know, various concepts, air, sulfur, there's some others that seem like they still have a long way to go. So I think that would be my sense is that developing a practical cathode, either high voltage or high capacity, is the biggest bottleneck that I see.
Yeah, I'd agree with that. You know, the next material that has capacity that matches that of the graphite anode would be, I think, a winner. And so getting to higher gravimetric energy densities at the cathode side it's going to be very critical. Given that we have so many questions, I'm going to keep on just powering through here. And I'm going to take this next question, given its relevance to my prior research career in batteries. So question is, any idea why aqueous sodium air batteries have not gained as much traction as lithium air? It seems like people don't consider the water of salvation needed for some reason. Also, any idea why there's a focus on non-aqueous lithium and sodium air batteries over aqueous? Yeah, there actually is, there are research efforts in aqueous metal air systems. The challenge lies in the fact that both lithium and sodium metal are highly reactive. Their potentials lie at a level where if they come into exposure with water, they immediately react with water and evolve hydrogen. And so both sodium and lithium, if you were to place them directly into water, there's a good chance that they would actually ignite. They'd catch on fire because of the release of hydrogen that's highly exothermic, and then due to the fact that you have heat and hydrogen together, you form an explosive mixture of gases. And so protecting lithium and sodium metal from an aqueous electrolyte would take some of the solid state electrolytes that Steve discussed to do so. Yet those solid electrolytes have to be mechanically robust. They can't crack at any point, because if you have a crack, then you immediately have a safety challenge associated with those batteries. And then the design of the systems themselves need to be considered for high energy density. So if you have a thin layer of a solid state electrolyte, and then you have an aqueous electrolyte in your cell, that essentially is considered dead weight in the design of a battery. And so you need to limit the total thickness of electrolytes. And in lithium ion batteries, this has been engineered in a way that's very impressive. The distance between electrodes in lithium ion batteries on the order of 10 microns or so. And so all of these are kind of challenges with aqueous batteries. You need aqueous electrolyte, but you also need a solid state electrolyte. And so designing a geometry that allows that to occur while still maintaining a very thin distance between the electrodes is really, really difficult. And the reason that non-aqueous electrolytes have been focused on more than aqueous chemistries is that there are some non-aqueous electrolytes that are at least modestly stable to both lithium and sodium. You can have them in contact with each other, and there's an interfacial layer that forms that protects lithium and sodium metal to a modest degree. It's not as good as graphite in a lithium ion battery, but you still can at least make a battery in a very similar geometry as a lithium ion battery as a result. So that's why non-aqueous electrolytes have been primarily focused on. It's just an ease of assembly coupled with less of a safety hazard with having an aqueous electrolyte in the presence of lithium metal or sodium metal. Yeah. Okay, well, let's go to the next question here. And Anouck, I'll have you answer this one. Does battery research foresee the development of an energy storage option that could be used across the board? So for transportation, for grid storage, for electronic mobile devices, what are the benefits of battery energy storage as opposed to other methods like nuclear energy?
Okay, so I guess for the first part, I think it's really tough to just choose one battery for all uses. I think it's not one size fits all at all. So I think if you look at solid state batteries and lithium ion batteries, which is what most of the other panelists are focused on, those are clearly directed towards portable electronics, whether cars, computers, all of that. I think they are designed to be light and portable, therefore they need to be highly energy dense. And so on. But then when you look at what the requirement is for grid scale storage, you don't really care if it's light and portable because you kind of just need it to be there, just like one big battery that's there, that's plugged into the grid or plugged into a solar farm or plugged into a windmill, something. And so if you think about those design considerations, then all of a sudden you have a different set of building blocks and tools. And that's why, I mean, not to make a plug for grid scale, for redox flow batteries, but I think that's just an example of a battery whose design is totally opposite to lithium, in that you now have this modular design, tanks that can be scaled, and you're separating the power from, you're separating the size of the tanks from the cell, which means that you can kind of engineer it to your will. So you're not limited by, you're not limited in a way that lithium is, and you're not limited by size and weight. And that the same goes for non-electrochemical storage. I think there's a lot of really interesting, like compressed air and stuff like that, which you could never use in a car. And same with redox flow batteries, you couldn't really put them in a car. They're just huge and heavy, but they were designed to be that way because it doesn't matter for them to be portable. So yeah, I hope that answers the question. Long story short, it's not one size fits all. And I think the future looks like a bunch of different battery architectures and design kind of working in tandem on specific uses.
Yeah, absolutely. I agree with that. Well, it looks like we might have time for one more question. And so I'll leave this final question. Let's say, Amy, let's have you take this. We haven't talked about battery recycling yet. And so what are the efficiency of current battery recycling? So lithium and cobalt more specifically. And what are the prospects for efficient recycling of other battery types?
Well, I don't actually know the current efficiencies for lithium-ion batteries recycling. And part of that is because it hasn't been adopted very widely. There are people working on the very fundamental research of separation and purification to do that better. I mean, if you think about something like lead acid batteries, we recycle the lead in those batteries at greater than 99% efficiency. And some of it is that I think the separation challenges are a little bit more straightforward there. But a lot of it was, that was driven by a very widespread concern for lead toxicity. And so there was an incentive for the technical community to solve that problem. So I think if there were a similar incentive in lithium-ion batteries, I don't see any technical barrier to achieving those kinds of efficiencies. But Steve may know better than I would there.
I would just mention that in the lead battery field, all the form factors are pretty much the same, or there's only a couple of them. That helps. Also, the chemistry is the same for all, pretty much. That helps. But the biggest problem in my mind is that the recycling problem won't really rear its ugly head for 10 years or 15 years or 20 years when a lot of these, I mean, even now, there's just not enough electric cars that in 10 years, there's going to be a big demand. And so I think it's going to be hard to get a company to get serious about a problem that won't appear for 10 years, even if we had the technology today, and it doesn't seem like we do.
Yeah. Well, very good. Well, I think that that does it for us today. Thank you so much to our panelists for all of your thoughtful answers to these questions. And I apologize, I see we got about 30 Q&A questions here, and so we didn't get to many of them, and I apologize for not doing so. But thank you so much to the panelists and also the attendees for your interests in this topic. So I'll hand it over to Lo.
Yeah, thank you, Brian, and thank you, Amy, Anouck, and Steve for participating in today's panel discussion. It was a wonderful discussion. Yes, there's a lot of interest with a lot of questions. Let me offer this, since there were a lot of questions that we were not able to get to today. If you want to email us at COC for College of Chemistry _relations@berkeley.edu. We will forward these along to Brian, Amy, Anouck, and Steve, who can hopefully take a few minutes to give their perspectives on those specific questions. But thank you all for attending today's ecosystem talk. Again, we encourage you to look at ecosystems.berkeley.edu for past and future events. And also remind you to take 2 minutes to fill out our post-event survey and to provide us input on future events. We hope to see you again soon. Thank you again to our panelists. And as we say in Berkeley, go Bears.